created by order. Over the past 300 years, humanity has developed amazing ways to harness energy. And we have used this ability to transform our environment. But all the structures we see around us are just one type of visible order we have created on planet Earth. There is another, more complex type of invisible order that we are only now beginning to understand. It is something that nature has exploited for billions of years, something we call information. The concept of information is a very strange one. It is truly a difficult idea to rethink. But in the journey to understand it, scientists will discover that information is actually a fundamental part of our universe. This film is the story of information and the immense power released from manipulating it. It is the story of how we discovered the power of symbols in writing, how codes and computers would revolutionize our understanding of the universe. It is the story of how, in a collapsing and chaotic universe, information can be used to create order and structure. At first glance, information seems a very simple idea. It exists everywhere in our world. Our brains are filled with it, and we constantly exchange it with each other. But information is one of the most subtle and difficult concepts that science has grappled with. Understanding and harnessing it has been an extremely long and difficult process. The power of information was first seen over 5,000 years ago, when a revolutionary technology was developed, something that would set the modern world in motion. Over the years, humanity has devised some quite remarkable things. But among all human inventions, one truly stands out. It is the most transformative, groundbreaking, and creative technology ever conceived. And it is also one of the simplest. That invention is writing. The essence of writing is to convey and store information. The earliest writing we have is in the form of ancient cuneiform from the 3rd dynasty of Ur. Written on clay tablets, and it comes from Sumer in ancient Mesopotamia, present-day Iraq. By combining different sound images, the ancient Mesopotamians could express any imaginable idea. The essence of their breakthrough was realizing that, for example, the image of an eye and the image of a reed did not necessarily mean an eye and a reed. The images could be used simply for the sounds they produced. In this case, it meant idea. Once this system was discovered, it meant that anything that could be spoken, even the strangest or most abstract thoughts, could be turned into symbols. Information could now live outside the human brain, and this meant it could persist for a long time. It was an idea that fascinated the ancient Mesopotamians. By turning sounds into symbols, Mesopotamian scribes discovered that information could be very easily transformed from one form to another. From something existing as spoken sound to something existing as symbols on a clay tablet. But this was just the beginning. Humans had not yet realized the true power of symbols. For 4,000 years, writing was almost the only information technology humans used. But in the 19th century, during the Great Industrial Revolution, things began to change. In the whirlwind of ideas and inventions, a series of seemingly unrelated technologies would emerge. But all would begin to reveal the immense power of information. All these technologies had very practical, non-theoretical origins. But they would begin to reveal that information is a much deeper and more powerful concept than anyone had realized. One of the first products of information technology was developed in the city of Lyon, France, in the late 18th century. 18th century Lyon was home to some of the world's finest craftsmen. It was also an extremely luxurious, magnificent, and above all, wealthy place, thanks to the fashionable nobles and bankers who lived there. S largest silk industry, with nearly a third of the city. And it was a place with over 14,000 looms. The demand for Lyon's fine fabrics was huge, but the weaving process was very slow. However, thanks to a soldier and weaver named Joseph Marie Jacquard, a device would be developed to help speed up fabric weaving. In the process, it would reveal a fundamental truth about information. Building on the work of several others, in 1804, Jacquard was granted a patent for his invention. At that time, a loom was the most complex mechanism humanity had ever built. Jacquard's loom was a marvel of ingenuity. He designed a unique machine without any changes to its structure or hardware. Using modern language, it can be programmed to weave any pattern a designer can conceive. In fact, it can mass-produce silk designs simply by pausing production. Jacquard had found the holy grail of weaving, and the secret lay in a simple punched card. The punched cards contained the essence of the designs the loom would execute. When these punched cards were fed into the loom, they would lower or raise the corresponding threads, thereby reproducing the pattern on the silk. Any design you can think of can be analyzed and converted into a sequence of punched cards, and then can be woven by the loom. Information was converted from image to punched card, then into finished fabric. Jacquard revolutionized the silk industry, but hidden within was something even more significant. Something more universal. That was the origin of industrialization and the ability to accelerate information process. Now, it revealed the power of abstracting information. It showed that you could capture the essence of something, extract crucial information and represent it in another form. Writing had revealed that you could use a set of symbols to capture spoken language. Now, Jacquard had shown that, with just two symbols, a whole or a blank, you could capture the information of any imaginable picture. This is a portrait of Jacquard woven in silk. It is spectacularly detailed with hundreds of thousands of stitches. However, all the information needed to create this realistic image could be stored in a series of punched cards. Exactly 24,000 cards. This picture is a brilliant example of a truly profound idea. That the simplest system, in this case, cards with a series of holes, can capture the essence of something much more complex. If 24,000 punched cards could produce an image like this, what would happen if you had 24 million or 24 trillion cards? What new kinds of complex information could be captured and presented? Jacquard had inadvertently uncovered an immensely deep and broad idea. With enough quantity, simple symbols could be used to describe anything in the entire universe. Converting information into abstract symbols for storage and processing has proven to be an extremely powerful idea. But how information was sent, how it was communicated, remained unchanged for thousands of years. The world before telecommunications technology was a very, because you could only send messages as fast as you could transport an object. So, you would write a message on a piece of paper or something similar, and then hand it to someone, and that person could run very fast, ride a horse, or board a ship quickly. But the problem was you could only send information as fast as possible that way. However, in the 19th century, the speed of information transmission would increase significantly, thanks to an astonishing new medium, electricity. Not long after electricity was discovered, excitement grew about its potential as a means of conveying messages. It seemed that if it could be controlled and stored at will, then electricity would be the perfect medium for sending information. Electricity seemed to offer many benefits as a means of sending messages. It traveled through wires, meaning it could go anywhere. It was unaffected by bad weather conditions. And most importantly, it could move very fast. But there was a major problem that those wanting to use electricity as a communication medium in the early 19th century had. How could such a simple signal be used to send complex messages? This is one of the early devices designed to send signals by electricity. Developed in 1809 in Bavaria by Samuel Sommering. So if the sender wanted to send a letter A, it would send current through that corresponding wire. At the receiver end was a container filled with liquid, and the current caused a chemical reaction, making bubbles appear above the corresponding letter A. This entire process was clever, though somewhat laborious. But what's truly interesting is that the sender had to let the receiver know they were about to send a signal. He did this by sending extra current to produce more bubbles, forcing an arm to lift up to release a ball and trigger a bell. As you can imagine, this was not the fastest system. After sommering, all approaches were made to solve the problem. But sending messages by electricity, but they all suffered from complex codes. But these devices, each ingenious and innovative in its own way, were all destined for the scrap heap of history. And that's because, in the 1840s, they were replaced by a signaling method that still exists today. It was developed by artist and businessman Samuel Morse, along with his colleague Alfred Vail. What was special about their system was not the technology used to transmit the messages, but the extremely simple and efficient code they used to send them. Like Jacquard's punch cards. The brilliance of the Morse and Vail code lay in its simplicity. By using short and long electrical pulses, they could spell out every letter in the alphabet. Vail suggested that the most common letters in English would have the shortest codes. So an E was said like this, while an X was said like this. This meant messages could be sent quickly and efficiently. Thus, together they created an entirely new technology, the telegraph. The telegraph once again revealed the power of translating information from one medium to another. Information was initially fixed in the human brain, then expressed through symbols using stone, paper, and punch cards. Now, thanks to Morse, information could reside in electricity. And this made it lighter and faster than ever before. In just a few short years, the telegraph network spread across the globe, laying the foundation for the modern information age. Between them, Samuel Morse and Vail discovered new and novel ways to manipulate, process, and transmit information. What had begun with the invention of writing thousands of years ago reached a point where entire messages were forged in a network of wires carrying highly abstract information at astonishing speed. For those in the late 19th century, it might have seemed like the ultimate in humanity's ability to manipulate and transmit information. Information would reveal itself to be an even more crucial concept, more fundamental than anything we can imagine. Clearly, information is not merely for communication between humans, but also a concept with much broader and deeper implications. The true nature of information was first revealed through a strange problem. An idea sparked from the dream of a brilliant Scottish physicist, who seemed to be pondering something entirely different. James Clerk Maxwell was one of the greatest minds of the 19th century. Among his many interests, Maxwell was fascinated by thermodynamics, the science studying heat and motion, emerging alongside the development of the steam engine. Maxwell was among the first to realize that heat is essentially just the motion of molecules. The hotter an object, the faster its molecules move. This idea led Maxwell to a very peculiar thought experiment, in which information played a key role. Maxwell hypothesized that, simply by knowing what is happening inside a box filled with air, one could make one half of the box hot and the other half cold. Imagine heating an oven next to a refrigerator without expending energy. It sounds crazy, but Maxwell's reasoning was very compelling. It goes like this. Imagine a little demon with superhuman vision sitting on the lid of the box, able to precisely observe the motion of every air molecule inside. This demon controls a partition dividing the box into two halves. Whenever it sees a fast-moving molecule approaching the partition from the right, the demon opens it to let that molecule pass to the left. And whenever it sees a slow-moving molecule approaching from the left, the demon opens the partition to let it pass to the right. Now, you can see what will happen. Over time, all the hot, fast-moving molecules will accumulate in the left half of the box, and all the cold, slow-moving molecules will be in the right half. Crucially, the demon performs this sorting based solely on information about the molecule's motion. Maxwell's demon seemed to suggest that, with just information about the molecules, you could create order from chaos. This idea contradicted the prevailing 19th century notion. Thermodynamics had clearly demonstrated that, over time, the entropy of the universe, the degree of disorder, always increases. Everything seems destined to fall apart. But the demon hinted that you could rearrange things without expending energy. Simply by using information, you could create order. This turned out to be an extremely difficult problem to solve, at least partly because Maxwell had conceived an idea far ahead of its time. So what really happens with Maxwell's demon? It sounds distant and mystical. But imagine if we could build a real machine that could mimic the demon's actions. We could use it to heat a cup of coffee, run an engine, or power an entire city. 1. Everything uses only pure information, nothing more. 2. In that way, we can create order in the universe without expending energy. 3. Scientists had a hunch that this was wrong. 4. And it took over 100 years for the problem to be solved. 5. While Maxwell's puzzle continued. 6. Something quite unexpected happened. 7. People dreamed of a new device that could perform incredible 8. And complex tasks simply by processing information. 9. Moreover, this was actually a device that could be built. 10. That machine was called a computer. 11. And the idea behind it came from a brilliant and visionary scientist. 12. Alan Turing was the first to conceive of the modern computer. 13. A machine whose sole function is to manipulate and process information. 14. A machine that harnesses the power of abstract symbols. 15. A machine that can perform almost every aspect of the modern world. 16. Turing's astonishing idea first appeared in a legendary mathematics paper. 17. Published in 1936. 18. In his short life, Alan Turing contributed groundbreaking ideas. 19. To many fields, from cryptography to biology. 20. The scope of his thinking was truly extraordinary. 21. But for most scientists. 22. It was the concept he outlined in the 1936 paper that proved he was truly special. 23. It is this work that makes him worthy of the title of genius. 24. Published when Turing was just 24 years old. 25. The paper on computable numbers with an application to the Einstein's problem of mathematical law. 26. It is astonishing that the idea of the modern computer emerged. 27. Simply from Turing's brilliant reasoning ability. 28. Turing began to investigate whether certain mathematical procedures 29. Could be carried out just by following a set of rules. 30. And this is precisely what led him to think about computers. Computer. 32. It referred to an actual person with pencil and paper performing repetitive calculations. 33. Banks hired many such people, often women, to compute payments. 34. Tax agencies hired them to calculate tax amounts. 35. Observatories hired them to compute orientation data. 36. Human computers were crucial to the modern world. 37. Processing the vast amounts of information generated by science and industry was becoming increasingly complex. 38. What Turing did in the 1936 paper was pose a simple but profound question. 39. What goes on in the mind of a person performing a calculation? 40. To do this, he first had to strip away all extraneous details, leaving only the essence of a computational process. 41. So first, remove the ink, then the pen, ruler, pencil, and notebook. 42. All these things make calculation easier. 43. But none of them are actually necessary for the person performing the calculation. 44. Turing asked, what goes on in the brain of a human computer? 45. It is an extremely complex biological system, capable of perception, thought, and deep understanding. 46. But for Turing, none of this was important to the process of calculation. 47. Turing realized that to compute something, one must follow a set of rules precisely. 48. That's all. Turing saw that every calculation has two aspects. 49. Data and instructions on what to do with that data. 50. And this would be the key to his insight. Turing needed to find a way for machines to understand commands like addition, subtraction, multiplication, just like humans do. In other words, he had to translate such instructions into a language that machines could understand. With brilliant logical thinking, Turing accomplished exactly that. To humans, this might look like a random string of ones and zeros. But to a computer, it is a set of instructions that can be read step by step, requiring the machine to operate in a specific way. So, while humans can look at this notation and understand the necessary process, the computer must interpret it like this. The paper Turing used is what we now call computer memory. But Turing didn't stop there. Turing realized that giving instructions to a machine in this way yielded an astonishing result. It meant that a single machine could perform almost any task you could think of. It was an incredibly simple and beautiful concept. To make the machine do something new, all you needed to do was provide it with a new set of instructions. This idea, called the universal Turing machine, was the new information. The more you wanted the machine to do, the longer the paper tape had to be. Larger memory could hold complex, multi-layered instructions on how to process and organize any imaginable type of information. With enough memory, computers would be capable of performing countless tasks. Turing's idea that countless different tasks could be accomplished simply by giving the computer a long sequence of instructions is his greatest legacy. Since his paper, Turing's dream has become a reality. So, computing, making phone calls, recording moving images, writing letters, listening to music, none of these require a separate machine. All can be done on a single device, the computer. Today's smartphone is the embodiment of that brilliant idea. Inside it are countless instructions, called programs, software, or apps. They're essentially just a long string of numbers telling the phone what to do. That's astonishing about Turing. Sets of instructions can be fed into a computer, enabling it to know how to mimic a telephone or a typewriter. We can even describe natural laws, physical principles, or processes occurring in the natural world. This is a simulation of millions of particles behaving as a fluid. To understand how it works, the computer simply follows a set of instructions stored in memory. This only hints at part of the computer's power. This is a computer simulation of the large-scale structure of the entire universe, and it shows the true power behind Turing's idea. Turning instructions into symbols that machines understand allows us to recreate not merely an image or a sound, but a process, a system, something that is changing and evolving. Using simple symbols, computers have the ability to capture the essence and order of the natural world. By contemplating how the human brain processes and computes information, Alan Turing had one of the most important ideas of the 20th century, revealing the power of information. It's easy to think that after Turing, the true power of information was unleashed, but Turing is only half the story. The modern information age will require another idea. A final concept will define the nature of information and its relationship to order and chaos in the universe. It is an idea nurtured by a talented and eccentric mathematician and engineer. Claude Shannon was a truly unusual person, and his designs to solve unusual problems would lead to a revolutionary new idea. The concept that will explore the fundamental nature of information and the process of communication in all its diverse forms. This is Claude Shannon's paper, A Mathematical Theory of Communication. The title sounds dry, but it is one of the most important scientific papers of the 20th century. It not only laid the foundation for the modern global communication network, but also gave us new insights into human language, into things we often do intuitively like speaking and writing. The paper was published in 1948, when Shannon was working at Bell Labs in New Jersey, the research division of the vast Bell Telephone Corporation. It was an organization famous for its progressive thinking, relaxed atmosphere, where mathematicians were free to tackle any problem they were interested in. Claude Shannon was given free rein to do pretty much whatever he wanted. The Bell telephone network was facing a huge problem at the time. Every day they transmitted a vast amount of electronic information across the world, but they didn't really know how to measure or quantify this information accurately. In short, their entire business was built on something they didn't truly understand. Surprisingly, their superstar employee, Claude Shannon, provided exactly what they needed. In his paper, Shannon achieved something utterly astonishing. He grasped the vague and mysterious concept of information and attempted to define it. He didn't do this using some cleverly phrased philosophical definition. He actually figured out a way to measure the amount of information contained in a message. Surprisingly, Shannon realized that the amount of information in a message had nothing to do with its meaning. Instead, he pointed out that it was only related to how surprising the message was. Information must contain surprise, because news is news because it is surprising. And the more surprising it is, the more newsworthy it is. News is the same as yesterday. So there was a relationship between surprise and information. But Shannon went further and created his own unit of measurement for information. So how did he do this? Shannon showed that any message you want to send can be translated into binary code. A long string of ones and zeros. Shannon realized that converting information into binary code would be an incredibly powerful act. It would make information manageable, precise, controllable, and clear. In his paper, Shannon showed that a binary digit, one of these ones or zeros, is the basic unit of information. Think of it as an atom of information, the smallest possible piece. After defining this basic unit, he even gave it a name that we are all familiar with today. Binary digit. And this seemingly humble thing turned out to be an incredibly powerful idea. The power of the bit lies in its universality. Any system with two states, like a coin with heads or tails, can carry one bit of information. 1 or 0, yes or no, on or off, stop or go. All these systems can store one bit of information. Thanks to Shannon, the bit became a common language of all information. Anything, sound, images, text can be converted into bits and transmitted by any system capable of existing in two states. Shannon introduced a new theory with profound and far-reaching influence. The ideas he began to explore would form the foundation of what we now call information theory. He took an abstract concept, information, and turned it into something tangible. What was once just a vague, immeasurable concept became something real. The idea of converting everything into bits to digitize it fundamentally transformed many aspects of human society. But information is not just something humans create. We're beginning to understand that this concept lies at the heart, not only of 21st century human society, but also at the heart of the physical world itself. All the information we have ever created, every book, every movie, all the content on the internet is almost nothing compared to the informational content of nature. And that's because even the most mundane event contains a spectacular amount of information. Imagine how much information you would need to describe this. The magnificent and complex interaction of physical laws occurs on scales and timeframes we often cannot perceive. But here, we're still only seeing a tiny fraction of nature's complexity. Imagine the interaction between trillions upon trillions of atoms. The number of bits you need to describe this is almost unimaginable. But the astonishing thing is that now, thanks to the ideas of Taryn and Shannon, we can describe, model, and simulate nature in more detail than ever before. But this is not the end of the story. It seems that information is not just a way of describing reality. In recent years, researchers have discovered that information is actually an inseparable part of the physical world. It is truly a difficult idea to grasp, but information, everything from a Beethoven symphony to the contents of a dictionary, even a fleeting thought, all information must be expressed in some form of physical system. Surprisingly, the reason we understand the true connection between information and reality is thanks to Maxwell's demon. Remember that it seemed the demon could use information to create order in an initially completely chaotic box. Moreover, it can do this without expending any effort. Information seemed to be able to break the laws of physics. To be right, it. What was discovered is this. The demon really uses nothing but information to create useful energy. But this does not mean it gets something for nothing. Remember how the demon works. It detects a fast-moving molecule on one side of the OS, opens a partition, and lets it pass to the other side. But each time it does this, it must store information on that molecule's speed in its memory. Soon, the demon's memory will fill up, and it can only continue if it starts erasing information. The crucial point is that this erasure will require the demon to expend energy. It is an irreversible process that increases the entropy of the universe. It is the act of erasing information that increases entropy once and for all. What was discovered is that there is a specific minimum amount of energy, called the Landauer limit, required to erase a bit of information. It is very small, less than 1,000 billionth of the energy in a gram of sugar, but it is real. It is part of the fundamental fabric of the universe. Surprisingly, we can now conduct actual experiments to test aspects of Maxwell's idea. Using lasers and extremely tiny dust particles, scientists around the world are exploring the relationship between information and energy with astonishing precision. Maxwell's thought experiment, dreamed up in the age of steam, is still at the forefront of scientific research today. Maxwell's demon links the two most important concepts in science together, the study of energy and the study of information. It shows they are deeply connected. What we know now is that information is not some abstract concept. It obeys the laws of physics, just like everything else in the universe. Information is not just an intersection, nor is it just some mathematics or formula you write on paper. Actually, information is carried by something, so it is embodied in something. A phone, a book, a CD. Anyway, there is always a medium for transmitting information, and that means information operates according to physical laws. So it cannot break the laws of physics. What humanity has learned over the last few millennia is that information can never be separated from the physical world. This is not an obstacle. What makes information powerful is that it can be stored in any physical system we choose. From using stone and clay tablets to preserve information across ages, to using electricity and light to send information quickly. The medium for storing information gives it unique properties. Today, scientists are exploring new ways to process information, using everything from DNA to quantum particles. They hope this work will usher in a new information age. Each bit transforms like the last. What we know now is that we have only just begun the journey of discovering the power of information. It is clear that creating material order, the structures we see around us, comes at a cost. We need to do work, to expend energy, to build them. But in recent years, we have realized that organizing information creates invisible digital structures in the modern world. Also comes with an unavoidable cost. Information once seemed abstract and ethereal, but now we know that it must always be expressed through a physical system. This is an incredibly fascinating idea. A lump of clay can be used to write a poem. Air molecules can carry the sound of a symphony. And a single photon is like a paintbrush. Every aspect of the material universe can be seen as a blank canvas, which we can use to create beauty, structure, and order.